All right, so far we have considered arrivals consisting of just one customer. We can also consider arrivals with groups, and this is called the compound Poisson process. So let me first illustrate what it means. So now we have, let's say, n arrivals. So this is the first one, okay, at a certain time over here, and t1, let's say. And then we have another at t2. So these are arrival times. And then we have over here tn. Okay, so these are arrivals. But in each arrival, we may have multiple, say, passengers. We say the size of the batches can be different. So here, probably we have, say, a group of 2, and here probably we have just a group of 1, and here we have a group of 5, like this. As long as we know what kind of distribution function we have for the number of, say, these groups over here, members in the groups over here, we can find out what is the expected value of the sum of these arrivals. And we can also find out what is the variance of the sum of all the members in these groups. But be careful, compound Poisson process is no longer a Poisson process. In fact, we don't have to have PMFs, the discrete random variables over here. We can have continuous ones as well. So YT here is the sum of all the batches over here. Can be just a real number, not an integer. But in our next example, we assume that we have actually discrete random variables for these members in the groups. So let's look at an example. So the arrival of passenger cars to a train station is assumed to be a Poisson process. So the arrival of cars has a Poisson distribution. No, it's a Poisson process with a rate of 5 cars per hour. So the rate is 5 cars per hour. But the number of passengers in each car is different, can be different, and it's a random variable. We assume that these random variables, they are independent. That means how many passengers in the first car, you cannot tell if you know the number of passengers in the first car, you don't know what's going to be the next. But we know the distribution of the number of passengers. So the probability that the car has only one passenger inside is 0.5. And having 2 is 0.3. And having 3 is 0.2. So add them up, it's going to be 1. So this is the discrete distribution function for number of passengers within each arrival. And now we are going to add them up. So y of t over here is the total number of passengers, is the total number of passengers arrived by time t. And we don't really know exactly what kind of distribution we have, but we know how to calculate the expected value and also its variance by using this formula. The derivation of these two formulas are omitted, so we are not going to derive these two formulas. So what do we have over here? Now, look at the question. Find the mean and standard deviation of the number of passengers that arrive at the station over an 8-hour period. So we have t is equal to 8 hour. And also we know that lambda over here is equal to 5 cars per hour. So we have lambda is going to be 5. Okay. So now, according to what we have, so the expected value of y8 because that's the number of total number of passengers arrived within 8-hour period, and it's going to be equal to mu, lambda, and t. So we need to find mu first. Mu is the expected value. So mu of the size of the groups, we have the value times the probability. So 1 times 0.5 plus 2 times 0.3 and plus 3 times 0.2. So we have 0.5 plus 0.6 and plus 0.6. So we have 1.7, and that's what we have. And then we plug in the value. So mu over here is going to be 1.7. That's the average size or average number of passengers in each car, and times the rate, which is 5, and times 8. So that's going to be 1.7 is 17 times 4, and that's going to be 68. So we can expect on average 68 passengers arriving at the station. Now, how do we calculate the variance? We have, again, mu already have, so we have variance of y8 by the formula. That's going to be mu squared and plus sigma squared and lambda t. And remember, sigma squared is the variance. That's the variance of x. And then we have variance is the expected value of x squared minus the square of the expected value. So we calculate this value over here. Again, so we have ex squared. It's a value, so it's 1 squared times 0.5 and plus 2 squared plus 2 squared times 0.3 and plus 3 squared times 0.2, and then we have 0.5 plus 1.2 and plus 1.8, and that's going to be 3.5. Okay, and we look at what's going to be ex squared, and that's, we already calculated, it's 1.7 squared, and that's going to be 9, 8, and 2. Okay, so that's what we have. And then what we have now is the following. So this variance is going to be 3.5 minus 2.89, and that's going to be a number that we can easily calculate, and if you want to use a calculator, that's going to be fine, and that's, if you can see, this is going to be just 0.61. Okay, so now we put them back. Mu squared we already calculated is 2.89. So now we have the variance of y8. That's going to be mu squared is 2.89, and plus this variance is going to be 0.61, and then we multiplied by lambda, which is 5, and then t is going to be 8. So this is the value we have. In fact, we can see over here, this is exactly sigma squared, because we see over there, this is going to be exactly sigma squared. So it's 3.5. No, it's 3.5 we see over here, and times 5 times 8, and that's going to be 35 times 5, 35 times 4, and that we will have 0 over here and 140. Okay, and that's the variance.